Welcome to the first of our videos on exploring mathematics. This is a weekly activity, and this week we looked at the Fibonacci sequence and the golden ratio. Okay, so this is basically what it's about. If you start with the basic Fibonacci sequence, you write down a pair of ones and you add them together to get 2. 2 plus 1 is 3. 3 plus 2 is 5, 5 plus 3 is 8, and so on. So you get the next term by adding the previous two terms together. And you can continue as long as you wish to. But you don't have to start with a pair of ones. You can start with, for example, here I've got a 2 and a 7, add them together to get 9. 9 and 7 is 16, and so on. And here we've got two very different numbers at the start, but as we keep going, we build the sequence up in the same way. Okay, but what is fascinating is it doesn't matter how you start this sequence. If you took one term and divided it by the previous one, the further along the sequence you go, the closer and closer that number will always be to a particular value, and we'll come to that in just a moment. So for example, if I did now 34 divided by 21, okay, so that's the 9th term divided by the 8th term, that will give me 1.61 something, okay, 1.619 something, I believe that one is. Okay, if I took 173 over 107, okay, that's from the other sequence below, and do that on the calculator, that gives me a number very close to that. It gives me 1.618, 1.616, that one. Okay, 1.616. Okay, and if I do this one here, it will give me something very close to this as well. And in fact, if I carried on each sequence a bit further, all of those would be 1.618 to 3 decimal places. Okay, and indeed any Fibonacci sequence would ultimately tend towards that ratio of 1.618, okay, dividing that term by that term, and so on. Now, 1.618 is a decimalized version of what we call the golden ratio. Okay, this is the Greek letter phi, and the golden ratio is 1 plus the square root of 5 over 2. Okay, and it has this value, as I say, which is to 3 decimal places 1.618. And interestingly enough, if you take the reciprocal of the golden ratio, in other words, you flip the numerator and denominator and get this, the value of that is 0.618. Okay, and that in itself is a unique property of the golden ratio. Now, the importance of this in nature is phenomenal. It occurs in so many places. We talked about the perfect rectangle where the sides are in the ratio 1 to 1.618. There are measurements in nature on animals and the human body which form the golden ratio. There are movements in financial markets which retrace every now and then according to the Fibonacci ratio or the golden ratio. We also have the numbers of veins in leaves on plants, the numbers of leaves on a tree. We have things to do with architecture, ancient architecture and art, where the golden ratio can be superimposed on images of these paintings and buildings. Okay, and certain key features appear in direct correlation with the distances projected by the golden ratio. Now, this is what we're going to do now. We're going to look at why this 1 plus root 5 over 2 emerges and where it comes from. So I've made a general Fibonacci sequence. The first two letters, or numbers rather, are going to be A and B. The third term is going to be A plus B. The fourth term is going to be B plus A plus B, which is A plus 2B. and the fifth term is going to be this one plus this one, which is 2a plus 3b, and so on. And I've built up the first 8 or so terms there, 8 or 9 terms there. Now, let's look at this ratio in more detail and see if we can explain what's going on. Now, what we're saying is that whatever happens as we go further along the sequence, if you divide that by that, or that by that, it always seems to be getting closer and closer to this magic number, this golden ratio. All right, so what we're going to do is we're going to call that ratio x. So I'm going to say let x equal, okay, let's say this term and this term. So it will be 3a plus 5b, okay, over 2a plus 3b. Okay, and what we're saying is that that is also very close to this one over this one, or this one divided by this one, or this one divided by this one. Okay, so we're going to call that the golden ratio. All right, now what I'm going to do is I'm going to just split this up now, and watch what I'm going to do. I'm going to split this into 2 fractions, okay, and I'm going to call it 2a plus 3b. Okay, so I split this up into 2a plus 3b, but then I've also got another a and another 2b. Okay, and what I've done is split it into 2 fractions which both have the same denominator of 2a plus 3b. Okay, like that, you see. So all I've done, if I could do this in reverse and take those 2 fractions there and add them together, I will get back to this one here, you see. And that can be written as, well, the first part, you see, is 1 whole one. So it's 1 plus, and this one here is 2a plus 3b and a plus 2b divided by each other, but the other way round. I've got the a plus 2b on the top and the 2a plus 3b underneath. And in other words, that's the reciprocal of the golden ratio. Okay, now that is really significant, and we'll just take one more example. Let's suppose we went much further up and did these 2 here. So we're now saying let's consider the case further up the chain when x equals well, let's go right to this one here, the end one here, 13a plus 21b. Okay, so now I'm looking at this division here, 13a plus 21b over 8a plus 13b. Okay, and what I'm going to do this time is split it up in exactly the same way. All right, and I'm going to say that can be written as it's going to be equal to, let's put it underneath here like we did last time. So I can say that x equals 8a plus 13b. So I'm taking out of the 13a here an 8a plus a 13b. Okay, but I've got left over another 5a, and to get from 13 to 21, I've got another 8b, you see. And all of that, each of those fractions are written over the same denominator as before, which is 8a plus 13b. Okay, which goes there and there. Okay, and the same sort of thing again. If I look at this first part, that's equal to 1 whole 1. And the second part is this part over this part, which is the reciprocal of the golden ratio, because that over that we're supposing is the golden ratio. So therefore that over that is the reciprocal, which is 1 over x again. Okay, so we have this equation appearing which says x equals 1 plus 1 over x. And now we're going to solve it. Now I'm just going to remove all of this stuff here for the moment. Just take that out the way, so I've got a bit of space to work with. Okay, so we'll take those to one side. We'll just clear out this bit that we don't need, and we're going to use that space now to make our proof of this golden ratio. So I'm just going to go across here now to do that, and I'll use a different color here. We'll maybe just make a box around it there like that. Okay, so you can see how that comes about. I think this is a really fascinating piece of mathematics. So what we've said is that x equals 1 plus 1 over x. Okay, now I'll go through this fairly quickly and teach you something about solving a quadratic equation. X equals 1 plus 1 over x. Multiply both sides of the equation by x, and you get this. X squared equals x plus 1. Okay, subtract from both sides x and 1, so you get x squared minus x minus 1 equals 0. There is a quadratic equation. Now we're going to solve this using a method called completing the square. And what I'm going to do is I'm going to say, right, I'm going to halve the 1 in front of the x. This is x squared minus 1x. So I'm going to do x minus a half, and I'm going to square it. Okay? Now x minus a half squared is equal to x squared minus x, because it's minus a half x minus another half x plus a quarter. Okay? But my equation said x squared minus x minus 1. Okay? And I've currently got plus a quarter. So what I want to do now, okay, is I want to change this around a bit so that I can write my original equation as x minus a half squared, okay, and I've got to take away this quarter which is left over, okay, and I've also got to take away my 1 which is still there, you see, and that equals 0. Okay, now this means that x minus a half squared, if I add the quarter and the 1 to the other side, gives me 5 quarters. Okay, that means that if I square root both sides, x minus a half, okay, without the squared in it, is the square root of 5 over the square root of 4, which is root 5 over 2. But because you can have two roots that when you square them they become positive, you can have plus or minus root 5 over 2. Add the half to the other side. It tells me that the value of x equals a half plus or minus the square root of 5 over 2. And what we can do to tidy that up is we can rewrite that as 1 plus or minus root 5 divided by 2 as a single fraction like that. Okay, I'll just make that a straight line. Okay, and that is the golden ratio. And we're taking the positive square root, so we're ignoring that minus sign underneath to find the golden ratio. Okay, and that is how we show that the golden ratio is 1 plus root 5 over 2. And with any of those sequences that we had earlier, I'll just bring those back in so you can see them again. I'll just take this out the way now, or move it away just to the side. Okay, if I bring those others back in again, if I can find them, there they are. Okay, if you carried on those sequences further and further, it means that if you took one term and divided it by the previous one, many places along, it would be more and more close to this exact value of 1 plus root 5 over 2. Okay, and as I said, it didn't matter what pair of numbers you started with, it will eventually, in fact, quite quickly after a few terms, start to converge towards this value of 1.618. Okay, so that was a summary of what we did in the first Exploring Maths session. I hope that was helpful. Do explore it further and find out what you can about Fibonacci and the golden ratio. Take care.